If we simply take a motor and put it in place of the engine, we have to basically triple the size of the battery and the motor and the charging infrastructure, all just to make that machine move. We've tested those core interactions more than 1 billion times. Billion with a B. When you look at a ball screw, if you take all those bearing components and then make them move with respect to each other, especially when they're loaded up, it's an absolute nightmare.
I'm picturing autonomous humanoid, really strong robots.
Yeah.
Fast.
Scary ones. I don't like to think about humanoids because those are the scary ones.
Hey, Jeannie.
Yeah, Bruce.
Where are we today?
Today we are at RISE Robotics in Somerville with Blake Sessions, CTO of RISE Robotics. Hey, Blake.
Hi.
Hey, Blake.
Welcome.
Hey.
Thank you.
So it's great to be back here. That last episode with the 10 was really interesting. People had a lot of comments and questions, and so we're coming back to do a deeper dive into the technology.
Yeah, so should we go over some of the things that we heard in the last week or so? That thing's got more parts in it than all the mechanics and moving parts inside a VCR. And honestly, I was expecting him to showcase some new innovative proprietary design in linear actuators, which actually are simpler than hydraulics. But instead, I feel like they just took all of the complicated parts from hydraulic and pulley systems, added their secret ingredient version of complexity, and what they're showcasing is the end result.
Well, they are complex, but the thing is, when you look at a RISE Beltdraulic, it actually relies on a very small number of unique interactions. And the more of those different kind of interactions that you have, the more likely something is to go wrong. And as a result, we have a lot of confidence in the tech. We've tested those core interactions more than 1 billion times. Billion with a B, across all temperature ranges, all environments, et cetera. So yeah, we do have a lot of confidence in the reliability of it. And part count can be deceptive. You look at a car, well, there's 30,000 parts in a car. You look at a bicycle, 800 parts in a bicycle. These are really reliable machines. Part count isn't really a good measure or a good kind of correlation with reliability. It's more about number of unique physical phenomena that are occurring within the system. If you look at a hydraulic system, they're actually a lot more complex under the hood than you might imagine. We have a JCB service manual to look at together, and what you'll find is that there are well over 1,000 parts in the hydraulic system that power that machine, and they all do something that's a little bit different. And as a result, sometimes when hydraulics leak, it's actually hard to find where it's leaking from. And then on top of that, you have the fact that hydraulics require cooling systems. And that's a real whammy because it means you have another couple hundred parts, maybe even 1,000 parts that are just there to manage the heat, to extract it from the fluid, and to carry it into the environment. And the thing is that our systems are so efficient that we don't have any cooling involved, which is really pretty spectacular. When you really kind of peel back the hood, really any motion control system is complex. It's a question of what kind of complexity and how it's managed.
Why not use what multi-million-dollar CNC machines use? Ball screws. Put a ball screw inside the tube and drive it from one end with a permanent magnet servo motor driven through a gear train for torque multiplication. It's very fast and very precise. You can scale that as small or large as you need. They're called linear actuators. Sorry, you're late to the party.
Oh, we are. I hadn't thought about that. No, ball screws are really fantastic devices. They're very good at what they do. They're very stiff. They're very precise. As you mentioned, they are operated in CNC machines all day, every day, and there are very good reasons for that. But the thing is that when you really look at a ball screw closely, what you'll find is a complex bearing interaction that is at the heart of that device. And it really comes down to the balls and the nut and the screw and how those components interact. And while they're really good in kind of carefully controlled environments, they are really not good once you kind of go outside of the window in any given direction. So they don't tolerate shock loads very well. They don't tolerate temperature extremes because temperature differences make for differences of stress within the working components. They don't tolerate side loads. So if you take a hydraulic cylinder, for example, and you let it wiggle, you kind of shock load it, or you let it, just the inertia of a movement, nothing happens because the fluid just kind of tolerates it and components kind of move. But when you look at a ball screw, if you take all those bearing components and then make them move with respect to each other, especially when they're loaded up, it's an absolute nightmare. And the nice thing about RISE Beltdraulics is that because they're belt-driven, we have a little bit of misalignment in the belt system as a result, but nothing like you'd find inside of a ball screw. So they're certainly good for industrial environments, but they're really not the answer for the markets we're targeting.
Could you build a super jammer with ball screws?
No, you couldn't. I mean, there are some parts of it that you might be able to. So some of the fine adjustment components of this machine, we actually are using ball screws. Mm-hmm. We're using Thomson ball screws for, again, fine adjustments, light loads, slow speeds. But when you're talking about really high power action, high loads, high speeds.
7,000 pounds?
50,000 pounds on the actuator itself, you just got to find a different answer. And one of the biggest differences actually is quite simply speed. Screws are speed limited, and we can actually show you this in a Parker catalog where when you look at service life for a ball screw, you say, well, you can't drive it too fast, you can't drive it too hard, you can't exploit multiple power features at the same time, you can't be outside of a 20 to 40 degrees Celsius window. I mean, there are all these constraints that are placed upon simply using a service life curve that is given to you with a ball screw device. And speed, again, is one of those just huge limitations. And the reason is quite simple. It's long and it's rotating, and you can only spin it so fast before it goes unstable. And the belts, by contrast, are rated up to about 100 meters per second flight speed, which means that's the speed of the segment of belt that is flying through space. We kind of leverage that down, so our cylinders can't go 100 meters per second, but they can go 3-4 meters per second.
Wow.
So yeah, there are definitely differences, and they're based on fundamentally different principles.
Okay, here's another comment. I'm looking for electrical actuator rods that can replace the rams and valve bank on an excavator. The reason an excavator can work without wrecking itself is because of the relief valves in the valve bank. Put the bucket in the ground and pull back on the dipper. If the ground is too hard, it doesn't break the machine. The relief valve for the control senses too much pressure and opens, allowing a bypass. This saves the machine from breaking. That is active relief, which I believe is not too hard to do with an electronic actuator.
Are your actuators going to break all the machines out there?
I don't think so. We absolutely do have passive relief systems in place, and it's one of my favorite parts about our technology is that we take more of a system approach. So ball screw actuators that we just talked about, they're very much like a packaged thing. You want point A, point B to move with positions and loads. We take more of a system approach, which is actually a lot more analogous to hydraulic power, to actual fluid power, where you have valves and pumps and cylinders and hoses and management features and accumulators, and you place them each where they can fit, and then you route it all together with fluid. So we are much closer to that than we are to ball screws, and I'll give you a few examples. We have these patented topologies of high force density actuation. Those are the cylinders. Those are arguably actually the simplest part. We also have a patented traction drive that requires no counterweight, so we can take motor torque and we can convert it into belt load at any kind of differential of tension, which is completely unique. We also have the unique ability to transfer power, belt-driven power, from a given frame of reference to any other frame of reference. So that's 6 degrees of freedom, X, Y, Z, delta X, delta Y, delta Z. Any movement of those frames, we can put belt power from here to there with no forces or differences of length imposed on the belt system between them. And that's reserved only for electric power and for fluid power. Those are the only two ways that we can presently do that as engineers, except for RISE Beltdraulics. So it's things like this. And then the last one, of course, is shock tolerance. So because we have a belt, we might as well route it somewhere else and then put a shock tolerant feature in there that, again, is analogous to a pressure relief valve. What is a pressure relief valve? Well, it's a poppet valve with a spring behind it, such that whenever the pressure acting over the area exceeds the spring preload, it opens. It's a really simple and a really effective concept, and we can do the same right in a Beltdraulic system.
Belts don't last forever. They need to be replaced periodically because they stretch.
That is definitely a problem with many belt systems. Something like a timing belt or V-belt drive is particularly sensitive to that. And the reason is that you have a belt that is running at high speed, and you have a low tension side and a high tension side. And if you get that tensioning wrong, you might get oscillations in the belt, especially because the teeth on a timing belt tend to create a resonance in the system, right? So the belts that we use are a little bit different. I think about them more as wire rope systems than actual belt systems. They're miniaturized wire ropes inside of a flat polyurethane jacket with no teeth, and as a result, we don't have these resonance issues, we don't have these tensioning issues, and these belts can just fly. I've already mentioned they can go as fast as about 100 meters per second. They are sealed for life. The oil is sealed into the jacket itself so that the wire rope is lubricated for its useful life. Meanwhile, the environment is sealed out. It takes all the good parts of wire rope, namely the inherent kind of performance of it, but it takes out the bad parts, which include things like the Hertzian contact between each of the individual wires of an exposed wire rope and the pulley surface that it rides on, right? Instead, you have this nice uniform jacket. It's true that polyurethane and steel are kind of old materials, but the way that they're assembled and the way that they're used, again, principally in elevators, as far as most other folks are concerned, they're just incredibly unique. Another feature of these belts is that they can operate at pressures between the pulley surface and the belt surface of up to about 1,400 psi, 1,400 psi. If that sounds like it's kind of in the range of hydraulics, that's because it is. And that's the reason that we're able to get these really, really high pressures operating for many millions of cycles.
Wouldn't it still be cheaper and just as effective to use an electric motor to power a traditional hydraulic system? Servo has a huge disadvantage of having a motor sitting right by each element, whereas in hydraulics, I can use 5 of these with just one motor 20 meters away. Yeah, not at the same time, but in many scenarios, that would be a more efficient solution.
So the suggestion is to take a legacy hydraulic system, which principally includes a diesel engine, a hydraulic pump, a hydraulic distribution mechanism, valves, accumulators, cylinders, and to put a motor in place of the engine. This is typically called hydraulic over electric. And what that means is that the motion control system, the thing that is animating the machine, is hydraulic, and it's operating on an electric power supply, like a battery, right? So this is definitely the easiest thing to do. I think 1 or 2 of the comments kind of said, wouldn't it be easier too? I mean, the answer is yes. Putting a big motor in place of a diesel engine is something that we are doing all day, every day, right? But it does come with drawbacks, and I want to first start with an analogy here. Let's look at electric cars, because this trend has been happening in electric cars for some time. Just question to the group. Does anybody know how efficient the drivetrain of an electric car is? From the motor shaft, the output of the motor or the engine, to the wheels? Take a guess.
No idea.
It's a hard question.
Cars are really efficient. You have some loss in the transmission, you have some loss in shafts, you have some loss of the tires themselves. But generally speaking, you're delivering about 90% of the power that is coming out of the engine shaft to the wheels. 90% is pretty good. If that drivetrain were instead, let's say 30% or 35% efficient, all the power coming from the engine or motor, 2/3 of it is just gone before you ever get to the wheels. And the result of that would be that the batteries and the motor both, and everything that charges the batteries, have to triple in size. So we already have enough of a challenge trying to fit existing battery technology into a car, both from a cost perspective and from a literal size perspective. Let's try to triple the battery size and see if anybody would even raise their hand to say, I'm broadly interested in an electric car. I don't think we'd get any takers.
Yeah, the batteries are expensive.
Batteries are, exactly, they're by far the most expensive part. And that's precisely what we have with these other machines. These hydraulic power distribution systems are about 30 to 40% efficient. It's true that there are more efficient hydraulics out there, but they're not on these machines. And so if we simply take a motor and put it in place of the engine, we have to basically triple the size of the battery and the motor and the charging infrastructure, all just to make that machine move. And guess what? It's actually not the actuator cost or the cylinder cost that's preventing electrification in machines. It's the battery cost and the grid infrastructure behind it that are the really big challenges to solve. So it's really kind of night and day from that perspective. If you put RISE Beltdraulics on your machine, 90% mechanically efficient, you lose some to the motor, but really you are reducing by 2/3 the requirement for batteries, for charging infrastructure, and for motors. And it's not only a cost or a size thing, it's also an environmental question. Because if you need 3 times the batteries, you now need 3 times the lithium. If you need 3 times the motors, you're looking at 3x the copper, or maybe even neodymium if it's a brushless DC motor. So these are all real kind of material limitations that make it such that just dropping a motor in place of a diesel engine is actually a really tricky thing to do. So the question is, would we rather spend another $1,000 on the actual cylinders themselves and save, $100,000 over here on the infrastructure, the motor, the batteries, all of that together, not to mention the variable costs of the depreciation of the battery over time and the electricity itself that is used to power these machines? Or do you want to just pay a little more for the cylinders and just get it right from the beginning? I mean, it seems pretty clear to me.
Well, and over there on the outside, on the utility side of the meter, you have to deal with the utility.
Right. So I wanted to look at just the motor cost, because I think that's the biggest kind of hang up in people's minds is they say, well, let's say you have a small skid steer. This is kind of a small machine. It's got 2 tracks. It's got a boom. It's got a bucket. These are common machines. We've seen them plowing snow, picking stuff up, lifting dirt. But people's big hang up is you have more motors. Doesn't that mean it just costs way more? Well, let's just dig into that particular one just for a minute. Let's say that you have 4 cylinders on this machine, and each one has a 10 kilowatt requirement. So 10 kilowatts of power is being conveyed out of that linear actuator when it's being used. 2 for the boom and 2 for the bucket. Each of those cylinders is not operating very often, something like 10 to 25% of the time is kind of a range, just to give you an idea. But if you power it hydraulically, again, hydraulic over electric, meaning a big motor that is powering a pump that is then distributing that hydraulic fluid out to the cylinders, you have to account for the inefficiency of that hydraulic system, and you're looking at something like a 30 kilowatt requirement for that one single motor. and it has to operate all the time because it is passing power to each of the cylinders, and that power is kind of changing hands. And so you're looking at about 30 kilowatts of total installed continuous motor power on that machine. Now let's consider RISE Beltdraulics in place of that same hydraulic system. We have the same 4 cylinders. Each of them has about 10 kilowatts of requirement, but because they're not operating continuously, because they only need to be delivering power 10, 15, 20% of the time, the motors can actually be radically downsized. So to give you an example, something like a 3 to 4 kilowatt motor will be able to deliver 10 kilowatts of power a small fraction of the time. So each motor on one of these machines is 3 to 4 kilowatt kind of continuous power class. You still have 4 of them. Now you're looking at 12 to 16 kilowatts of total motor power on the machine. So yes, there are 4 motors instead of 1, but when you add up all the powers together, we're undercutting the hydraulic motor by about a factor of 2. And motors are often priced on a per kilowatt basis. So if you have a 10 kilowatt motor versus a 5 kilowatt motor, expect to pay about twice as much. I mean, it's not quite linear, but you can get a kind of broad idea like that. So they're just alone in the motor cost, we will actually spend less on motors with RISE Beltdraulics than the single hydraulic motor that would be on that machine. And then on top of that, because these motors are distributed and each of them is significantly smaller, remember 3 to 4 kilowatts versus 30 kilowatts, they're much less likely to require liquid cooling. So air-cooled motors, they're small. As you scale a motor up, you have surface area to volume working against you because the core of the motor, the stator, is generating heat, and you got to get rid of the heat, right? So when you have smaller motors, because they have higher surface area to volume or lower volume to surface area, you can find air-cooled motors more often, which means we are vastly more likely to be using air-cooled motors, meaning no cooling system, no radiators, no hoses, no valves, and none of the associated cost, waste, space, any of that. So just to kind of summarize it, one 30 kilowatt motor versus 4 3 to 4 kilowatt motors is actually a massive capital savings, even though it kind of seems like, oh, you got 4 instead of 1.
And if you're talking about a machine that's moving all these things around, you save all that weight too.
Absolutely.
Hydraulic systems have one advantage that nothing can compete with. Liquids don't compress and stretch like air and belts. Here's another one for you. The potential energy recovery regen from lowering is very useful. Hydraulics also are dangerous. A high pressure leak can literally cut a person in half. Don't existing robots use belts? And lastly, I've been on a few jobs where the digging had to be very precise. On one side, you have a gas line, and on the other, you have a valuable structure, and you can't make a mistake. So you have to take your time and be careful. How much better would it have been to be able to move my bucket to each perimeter of my dig and lock the parameters so that the machine won't go past that mark? Then I could work fast without fear of making a mistake. Time is money.
True. So all of these relate to my favorite topic, which really comes down to speed and precision. If you look at warehouse automation, just to kind of follow that arc for a moment, we first started with warehouses, just kind of shelves and people and packing slips and all of that. Then we started to transition to Kiva. That was one of the first really innovative companies that started to automate warehouse operations. And they had these bots. They run around, they're pretty slow, but they get the job done. And since then, they've simply amped up the speed, cranked it all the way to 11, 12, 13, 14. So when you look at the endpoint of a system like Kiva, where has it gotten to, right? You still have a kind of open warehouse floor, there's some tracks, there's some AGV going on, but these robots are just absolutely flying. They're moving so fast you can hardly even see kind of what you're looking at anymore. They're moving so fast. And all of that is to get more stuff moved through, per unit time, per unit area to really increase productivity. Now, if you kind of turn the lens over to what our industry is, off-highway heavy machinery, construction, material handling, agriculture, those same things apply. It's how much stuff can you move, take, push around, et cetera, per unit area, per unit time. And really, when you look at what limits that right now, there are 2 big limitations. The first is simply human perception. Things can only move so quickly before people start to not grasp what's going on anymore. Related to that is kind of safety, obviously. And the second is simply fluid power. So when you push fluid through tubes, what you end up with is power losses that basically operate as the cube of the speed of that fluid, either volumetric flow rate or linear speed of that fluid. And so if you want to double your speed, you're actually octupling, 8xing your power loss in that system, right? So that limitation and others basically keep fluid power kind of around 1 meter per second as a top speed, which is pretty fast, and it kind of jives nicely with human perception. So you have this kind of overall limitation on the speed that these actuators can move at that is about 1 meter per second. But let's say we're electrifying this. Let's say we're automating it. Let's say we have a fleet of automated forklifts operating in a warehouse that are no longer constrained by safety, that are no longer constrained by human perception, and that are not driven by fluid power. Can you move them at 3 meters per second, at 4 meters per second? Why not? Speed is time, time is money. These are all kind of commensurate things of value. And this is really where RISE Beltdraulics just rocks it, right? Their belts, they can operate at about 100 meters per second with no resonance, no tensioning issues. Again, we have to kind of take that down by a factor of 10 to get to cylinder speeds that are viable. But we can make things fly. And on top of that, one of these questions is very astute, talking about fluid compressibility. We think about hydraulic fluid as being incompressible, or so we're told. Turns out that's actually not quite the case. And fluid is compressible. Also, the cylinder expands, balloons is the word, as you apply pressure into the cylinder. Also, the lines and the conveyance of fluid, all of that is pressurized too. You add that up, it's actually quite a lot of compliance. And it amounts to about 1 to 2% absolute max of the fluid column in the cylinder. So for example, if it's 1 meter of fluid within a cylinder and it's being compressed to about 3,000 psi, expect that load to move about a centimeter, maybe 2 centimeters. That's really pretty squishy, I would argue. And when you compare that to RISE Beltdraulics, we have these steel reinforced polyurethane belts. It's steel. It looks like rubber. It looks like something soft. But keep in mind, behind it is steel. So steel inside of these belts stretches only about 0.3 to 0.4% relative to that 1 to 2% when you load it up fully. And as a result, our cylinders are between 2 times and 5 times stiffer than a hydraulic cylinder. Why does that matter? Well, because compliance relates to frequency response. The squishier something is, if you think of punching a pillow, you can't get it to move very fast, you can't get it to accelerate very fast because it's too squishy. But the harder it is, the higher your accelerations go.
The faster you can punch it.
And the faster you can punch it, the faster you can make it move, the more accurately you can position something. So all of these things go hand in hand, and when you combine high precision with high speed, you can really do a lot. You kind of need both. You can't have one but not the other. And the problem with fluid power is it has neither. And fortunately for us, these belt systems, our RISE Beltdraulic systems, have both. If there is a human nearby, obviously we have to keep everybody's safety in mind. But for those systems that are truly autonomous, that are out in the world where there is no risk to human life or health, we can really make stuff move a lot faster than we are. And we should. Time is money, time is valuable. So why not?
These are being controlled by AI, right?
That's the other half of this. So, while we are building the hardware platform for something like an AI-driven forklift, there are many companies that are working on the AI side itself. So we kind of hope to partner with those companies to say, we'll do the hardware platform. Guess what? This can move 3, 4, 5 times faster than you're used to dealing with. Make use of it. Let's see the dollars fly on the productivity side of the equation, not just on the cost side of the equation. At the end of the day, it's easy to say things are simple or things are complicated, but really, when I look at motion control, everything is complicated. It's kind of the way that it is complicated. Are you using just a few key mechanical interactions and leveraging those along with some innovative ways to use belts to really kind of compete with the fluid power system? Are you looking at a ball screw system? That is a different type of complexity, unfortunately one that is kind of incompatible with a lot of the tough applications that hydraulics excel at. Or are you dealing with fluid power? An interesting topic that I didn't touch on, but I kind of wanted to, is that hydraulic fluid is actually quite finicky. So hydraulic fluid, it has a viscosity to it, and it can neither be too thin nor too thick, because in both situations, something happens. If it's too thick, it might not go through the valves properly, it might kind of just get jammed, it might not move at the right speeds. And if it's too thin, then it bypasses all of the seals and all the working surfaces that are within the valves, within the pump itself. So you need to keep viscosity constrained, and viscosity correlates with a temperature window. So basically, with every hydraulic system, you actually have a little window that's usually, let's say 20 degrees Celsius, where you have to keep it within that range, else stuff starts to go bad. And as a result, you have these enormous thermal management systems that are designed to keep it within that range, mostly to cool it, because it loses so much energy to the environment that you just got to keep it cool. But
you have to heat it up to get it started.
Right, so that's the other side of this. So there are companies that will say, like, we have a 90% hydraulic system, and that may be true in limited circumstances, but then you have the opposite problem where your fluid's too cold. It's not even fluid enough to work, right? So in both cases, you have these kind of issues to manage with fluid. I'm going kind of deep on a tangent here, but at the end of the day, to get back to the main point, we're talking about some sort of complexity. The question is, what is it? What are its characteristics? How is it managed? Can we maintain things proactively? Can we maintain things intelligently? Or are we just going to wait for something to break? Are we going to replace things periodically because we know that the mean time to failure is 3 years, so we'll replace it every year just to put a factor of safety on that? I mean, all these questions matter, and there were some really good questions in this comment thread, so I'm really glad that people were able to poke at us and kind of give us some stuff to respond to.
Yeah, thanks for taking all this time and explaining this. I really do feel like this is the future.
Yeah.
We do too, or else we wouldn't be here, so yeah.
So Blake, what are we looking at?
So in front of us, we are looking at a Generation 2 prototype of a double-acting cylinder. This is something that we actually just got together relatively recently. It's also being shown at Bauma, for those who know what that show is. So it is a double-acting cylinder. That means it can push and it can pull. Beyond that, it can be configured to be double-ended, which means that it has a rod coming out that side and out this side as well for steering applications. So this one presently is configured to have just a single rod, but it can easily be adapted to be a double rod, double acting cylinder as well. And this one is actually direct drive. So I think I remember one of the comments being around gearboxes. Gearboxes are among my least favorite parts of our system, and that's because they are power limiting and they're expensive and they have a lot of precision parts inside. And the thing is that when we want to go really fast, we need a lot of power. And in this case, what you'll find is that this motor is driving the belt system directly. So there actually is no gearbox that is kind of intermediating that transaction, if you will. And thus, not only will it fly, it also reduces cost, it reduces complexity. So let's have a quick look at this double-acting Generation 2 cylinder. We're going to show it at about 500 millimeters per second. That is about a sixth of its actual maximum operating speed. But as I had just mentioned, we just got this together. So it's a benchtop prototype. It's fresh off the press, if you will. And another feature that is just kind of worth mentioning and worth looking at is that there is no reeling system on this at all. So it is simply a motor, a traction drive, and then our high force, high power density cylinder topology inside of this case that we're looking at here.
Great.
Davis, let it rip.
Cool.
All right. Very cool. We're able to see both the speed and the precision aspects that we were talking about. We are here to make things move quickly and precisely and efficiently, obviously. And we're excited about it. So if you're interested, have a look. We still have a WeFunder campaign that is live. It is pretty quickly selling out. It's almost at 100%. So if you're interested, please check us out at wefunder.com/RISE Robotics.
Great. We will. Thank you so much.